Welcome back to the class of electrochemistry. So, in the last lecture we started with galvanic cell and we learned how to represent the half cells and maybe one or two example we have given, and we will continue with that. Now, as far as the cell potential or cell EMF is concerned, I already discussed how to measure the cell potential. It is basically by means of a compensation method which is called the Poggendorff's compensation method, that you should use a standard cell of known EMF and then compare that with your unknown cell with the help of an arrangement which is known to be Poggendorff's compensation method. So, it is basically you have an external battery and then you have one resistance and then you have one standard cell and you have another unknown cell X, and this is your standard cell, and then you connect through a galvanometer by this, or maybe the same arrangement over here. So, whenever there is no deflection against maybe a certain point in this resistance, it is basically a wire, a long wire, and then you are connecting with one wire where this galvanometer is connected. So, this is generally nichrome or similar wire. So, when this one is having no deflection and this one is having no deflection, then the corresponding lengths will be basically proportional to the potential difference or EMF of this cell, and then taking the ratio you can find out this cell potential. Now, why this arrangement is made? Because EMF is the reversible cell potential. So, if you use a common voltmeter, so it is going to, in order to have a deflection in the voltmeter, you need to supply certain amount of additional current. So, that will be drawn from the cell, and reversibility of the cell will be lost. So, that is why in order to have this reversibility in the cell reaction, we need to use this method. So, therefore anyway, so cell E cell is phi right minus phi left when we use the reduction potentials. So, let us take one example for a given chemical reaction. How can we represent the corresponding the cell, that is the corresponding galvanic cell. So, let us take the example Cu solid plus twice Ag plus in solution phase, that gets you Cu2 plus twice Ag solid. So, this is the oxidation process and this is the reduction process. Okay, so, redox, these are the coupled process. So, we know that at cathode which is generally written as the right hand electrode. So, reduction is taking place. So, the reaction will be 2 Ag plus twice electron, that gets you 2 Ag solid. Anode, it is a left hand electrode, it is oxidation and the reaction will be Cu solid, that gets you Cu 2 plus twice electron. Okay. So, corresponding half cells will be represented like this, like Ag plus, Ag solid, and here it is Cu 2 plus. Okay. So, therefore, you couple these two, and so therefore, you have to put this in the right hand side and put this in the left hand side. So, your representation for the cell will be Cu 2 plus, then double vertical line, because this solution and the other solution okay. So, this is your left hand electrode, this is your right hand electrode. Here you have oxidation, here you have reduction. Okay. So, therefore, this is typically the representation. I mean, this way you are representing this particular chemical reaction, that this chemical reaction is going to, if you want to have this overall chemical change like this in a cell, then you need to construct the electrochemical cell like this. Now, let us come to Daniell cell, with which we started our discussion. So, Daniell cell, in that case the representation for Daniell cell will be zinc solid, zinc sulphate, concentration may be unity or something else, then CuSO4, concentration may be 1. For simplicity, I am taking concentration to be unity. So, this is the representation for the Daniell cell. For the earlier one, the earlier example, your E cell will be here, E cell will be equal to phi right minus phi left, that is equal to phi Ag plus Ag minus phi Cu 2 plus Cu. So, it is in conformity with the UPAC convention. Okay. So, for here it is you can represent in the same way. Now, next is the we have two half cells like this one, and these are appropriately connected like with the help of a salt bridge. Then the system is ready to go for for this for getting some electricity out of it. So, but next is how to find out the half cell, this half cell or that half cell potential. Okay. So, in order to, because we do not know what will be the potential, but the point is, using Pogendorf's compensation method, we can find out the cell potential. So, cell potential is basically potential difference between these two. So, then in that case, what will be the contribution from this one and what will be the contribution from this one? If we would like to know, then we would need to compare its potential with respect to some standard potential, that is the potential of another half cell whose value is already known, okay, or whose value is assumed to be something. Okay. So, that is typically the goal. Okay. So, therefore, measurement of half cell potential. In that case, we need to take the help of a standard half cell. which is called the standard hydrogen electrode or standard hydrogen half cell. Okay. So, it is basically represented like this: Pt solid, then H2 gas at 1 bar, P 1 bar, then H plus, that means acid aqueous, it is 1 molar, maybe 1 molar HCl. Okay. And at all the temperatures, when this condition is maintained, at all the temperatures, this phi is assumed to be equal to 0 at all T, provided this condition and this condition is maintained. So, it is a platinum solid. Now, basically it is a platinum wire or platinum plate on which the finely divided platinum particles are coated. So, it is platinized platinum electrode. So, the pictorially I can draw like this. You have this so you have platinum wire, platinized platinum wire, and this is 1 molar HCl, and hydrogen, pure hydrogen gas is bubbled over here. Okay, is bubbled over here, so that the solution is saturated with hydrogen, whatever may be the solubility of hydrogen, it is saturated with hydrogen, and this is called the standard hydrogen electrode. At all the temperatures, it is its phi value, that is the half cell potential, is assumed to be 0, and the half cell reaction goes as follows, like H plus electron, that gets to half H2 gas 1 bar. Okay. So, this is the reaction. So, therefore, what we have to do, if you want to know the half cell potential for this, then couple this electrode with either this one or with this one. That means, you construct the cell, construct the complete cell where one electrode, one of the two electrodes will be this standard hydrogen electrode, and then find out the EMF of the cell, maybe at say 298 Kelvin, and then this EMF will be exactly equal to the unknown half cell. I mean EMF will be the potential for the unknown half cell. Okay. So, briefly what is done? You couple this hydrogen electrode like this. So, I shall abbreviate it like SHE, and then you have this double vertical line, then the second half cell, and then so this is, think that this is anode, that is put in the left hand side, and this is maybe cathode, it is the right hand electrode, and this is left hand electrode. Okay. So, the anode reaction goes like this: H plus electron, that gets you half H2 gas 1 bar, and the right hand reaction will be, right hand electrode reaction will be the reaction of the electrode whose half cell potential you would intend to find out. Okay. So, that means you will be able to find out the reduction potential reduction potential of the right hand half cell. Okay. So, in this case the concentration of the electrolyte, so concentration of the redox active substances may be or electrolyte associated with the electrode is said to be set at unity. Okay. And then the cell potential. So, if you keep this like this, then the cell potential or EMF or cell EMF is equal to the standard electrode potential or the standard reduction potential or standard reduction potential of the half cell in question. So, therefore, what you can write is basically E 0 bar, that is your standard value, is phi 0 bar right minus phi 0 bar left. Okay. Now, this one is equal to 0. So, therefore, E 0 bar is equal to phi 0 bar right. So, this way you can find out the standard reduction potential of the unknown, I mean of the half cell whose this potential, half cell potential is not known. Okay. So, therefore, suppose we do not know for the Daniell cell, we do not know the half cell potential for this half cell, say Cu2 plus. What you have to do? Just couple this with standard hydrogen electrode. So, it will be SHE, your constructed cell will be SHE, then Cu2 plus 1M, then Cu solid, Cu metal. Okay. So, more explicitly, PT platinum solid, it is the platinized platinum electrode, then you pass hydrogen, pure hydrogen gas at 1 bar pressure and say put so do the reaction or do everything, all the measurement at say 298 Kelvin. Okay. So, 25 degree centigrade. So, 1 bar, then H plus aqueous 1 molar solution. Okay. So, this completes the standard hydrogen electrode part, and it is your right hand electrode where this is your left hand electrode, this is the left side you will be putting. You can also put it in the right hand side. In that case you have to be careful about the sign, but anyway that is not the problem. So, anyway for simplicity we are putting the standard half cell in the left hand side and the unknown half cell in the right hand side. You can do in the other way, that is not a problem, that you have to do it every time that SHE has to be put over here. You can also put it over here and this one can be over here. Okay. So, left hand electrode, standard hydrogen electrode, and here oxidation is taking place. Now, couple this with the copper electrode. So, put a double vertical line Cu2 plus equals 1 m, then Cu solid. So, this completes the cell. This completes the cell that you have completed it, and then what you have to do, you measure the this EMF of this cell. Of course, this is 0. So, whatever value you will be getting as EMF of the cell will just be equal to this one, that is that will be equal to the reduction potential of this. Okay. So, that is why if you want to know the reduction potential of your unknown electrode, you should put that in the reduction side, that is your right hand electrode side, because the customary that it is that in the right hand side reduction is taking place, and the left hand side the oxidation is taking place. Okay. So, therefore, and if you measure at 298 Kelvin, you will be getting some value, and it is found that the value E cell, which is equal to phi right, which is found to be equal to 0.34 volt at this temperature condition. So, therefore, the reduction potential of this half cell is like this. Okay. So, therefore, this particular reaction, that is Cu2 plus equals 1 m plus 2 electron, that gets you Cu0 solid. So, that has got this much. So, this much of volt. So, if you want to express this in terms of delta G, then delta G will be equal to minus NFE. So, since E is positive, this E cell is positive. So, therefore, this delta G for the process, because it is E0. So, delta G 0. So, therefore, this will be positive. So, this side, so delta G 0 bar will be negative. So, therefore, this process will be spontaneous as it is represented like copper 2 plus to copper. It is a spontaneous process under this total cell reaction, where this is the half cell reaction. Okay. So, other side of the cell, I mean, is the oxidation of hydrogen to H plus. Okay. So, the total cell reaction, I mean this one, this half cell reaction plus this half cell reaction, if you add them together, then the corresponding delta G 0 will be less than 0. It is less than 0 means it is spontaneous. That means, if your cell potential or cell EMF is positive, then the net cell reaction is a spontaneous process. Net cell reaction is a spontaneous process. Now, similarly, what will happen for the, how will you get the value for, I mean, the half cell potential for this zinc 2 plus system? The same prescription is same, that you construct a cell, it is platinum solid, you couple with hydrogen electrode, H2 gas, then 1 bar pressure, then H plus aqueous 1 molar, then zinc 2 plus aqueous maybe 1 molar, then zinc solid. So, for this one, this is your left hand electrode, this is right hand electrode. So, if you measure the EMF of this cell with the help of this compensation method, I just have discussed a little bit. So, it is found that for this, the cell potential, since it is 1 bar, then 1 molar, so it is and 298 Kelvin. So, standard cell potential is found to be minus 0.76 volt. Okay. So, that means the half cell potential for this one, this particular reaction. Okay. So, reaction is like this, plus twice electron, that gets you zinc. Okay. So, half cell potential for this phi 2 plus is equal to minus 0.76 volt. Okay. So, what is the message? Message is your delta G is equal to minus NF E0. So, since this E0 is negative over here, so therefore, your delta G will be, this delta G will be greater than 0. So, basically it is a delta G at Tp is 0, I mean greater than 0 means it is I mean it is not a spontaneous process as it is represented, but the reverse process is spontaneous. Okay. So, therefore, what will happen? What will happen that now if we couple this together, what is going to happen? Although this half cell, if you consider this half cell only, half cell reaction, then this is not, I mean the way it is represented, I mean zinc 2 plus to zinc, it is with a negative value of potential. So, therefore, this reaction is not going to happen. What is going to happen is the other way around. Okay. So, therefore, what is the situation that therefore, the cell potential for this one is minus and the other one, that is for the copper one, is plus. So, now if you couple this two together, then the situation will be a little different. Okay. So, couple this together means if you couple, then your this Daniell cell. Okay. If you couple this together like this Daniell cell, okay, if you couple like this, okay. So, therefore, zinc solid, zinc sulphate is equal to 1, CuSO4, Cu. Okay. So, now you are putting this in the left hand electrode and putting this in the right hand electrode. What is going to happen? So, the reduction potential for this is what is the value? So, it is 0.34 volt and this is minus, it is minus, this value is minus 0.76. Okay. So, therefore, E cell will be phi right means Cu2 plus Cu minus phi left means zinc 2 plus zinc. So, that means 0.34 minus 0.76 volt, that gets you 1.1 volt. Okay. So, you see that when we add this appropriately, I mean when we combine these two electrodes, accordingly we add their respective reduction potential, then we get this value. Recall our earlier classes where we also have stated that its cell potential is 1.1 volt. So, 1.1 volt is coming, I mean the contribution is coming from this copper electrode and this much is coming from the zinc electrode. Okay. So, the positive value of the half cell potential, say for example, positive value of the half cell potential for say copper system Cu2 plus, Cu2 plus Cu, Cu2 plus say C is equal to 1, concentration equal to 1. So, indicates that, what does it indicate? It indicates that, so the reduction potential is is 0.34 volt, that means corresponding reaction is Cu2 plus 2 twice electron Cu0. So, the value of the potential is positive, means this process is spontaneous as it is represented. That means reduction is a spontaneous process for this. So, that is why this electrode is kept as the right hand electrode, okay. And therefore, copper can easily getting reduced to copper 2 plus can easily become copper 0, okay. So, so easily it can be reduced, but compared to hydrogen plus, okay. Why compared to hydrogen plus? Because we are calculating, we are estimating with respect to this hydrogen electrode, okay. So, that means H plus cannot oxidize copper to this process under the standard condition as stated, okay. So, therefore, that is why this copper does not dissolve in HCl under under normal conditions, okay. Now, in the other case, the negative reduction potential for zinc system, zinc 2 plus C equal to 1. So, minus 0.76 volt, okay. So, it means that the reduction potential for this system means that it indicates that H plus ion can oxidize zinc to zinc 2 plus, or zinc can reduce this H plus to H2, okay. So, that means reduction of copper to copper 0 by H plus is not possible, but you know reduction of H plus to H2 or oxidation of zinc to zinc plus, okay, this one is possible. That means this is negative, means we are representing the reaction zinc 2 plus twice electron zinc 0. So, for this is the value, this is negative, means corresponding delta G 0 is positive. So, the way it is represented, this is not a spontaneous direction, but the reverse is the spontaneous direction, okay. So, zinc will dissolve in HCl producing hydrogen. So, therefore, zinc will reduce H plus to hydrogen, and correspondingly or in other words in acidic condition zinc will be oxidized to zinc 2 plus, okay. So, therefore, that is why considering all that its reduction potential is plus 0.34 and its reduction potential is minus 0.76, we are putting this zinc electrode as the right hand electrode and the copper electrode as the left hand electrode, as I already have shown you the representation of the Daniell cell, okay. So, now we will now come to different, some examples of different types of electrodes. One example will be like hydrogen electrode, say for example hydrogen electrode, H2 electrode, okay. Hydrogen electrode is basically your standard hydrogen electrode, or maybe simple hydrogen electrode, okay. Or maybe say for example say chlorine electrode, or maybe bromine electrode. Bromine electrode is basically platinum, it is metal dipped into a solution like Br2 aqueous, then Br minus aqueous. Okay. So, this is called the bromine electrode, or maybe you can replace bromine by chlorine and chloride, it will be a chlorine electrode. So, basically the reaction is half Br2 aqueous plus electron, that gets to Br minus. Okay. So, this is in the reduction scheme. Okay. So, therefore, this is one electrode. Another may be like say for example, silver chloride electrode, like you dip silver wire in silver nitrate solution. So, it will be Ag solid, then Ag plus, say C equal to some value, that is a metal salt. Here it is gas, I mean platinum electrode, I mean hydrogen electrode, where hydrogen is basically in the form of gas. So, basically the equilibrium is H2 and H plus. Here it is Ag plus. In the same way, various other electrodes are also possible. Okay. So, therefore, this can be a representation. Also, maybe say for example, ferrous ferric system. So, what will you do? So, reaction is Fe3 plus electron, that gets to Fe2 plus. So, it is nothing but you have ferrous and ferric mixture and you dip one platinum wire into it. Or maybe say for example, you have other options like say one material which is reversible with respect to some ion, like say for example, silver chloride reversible with respect to chloride. So, what is the reaction? AgCl plus electron, that gets you Ag0 plus Cl minus. So, silver chloride reversible with respect to chloride. Okay. So, basically it is represented AgCl solid, Cl minus. Okay. So, its representation is like this. So, depending on, I mean whether it depending on its reduction potential, either it has to be put on the left hand electrode or maybe on the right hand electrode, so that the overall cell potential is positive, and as a result of which the overall cell reaction is spontaneous. But suppose if you represent in an arbitrary way, I mean you do not, suppose you do not care about where to place, I mean whether you will place the appropriate half cell in left hand side or in the right hand side, then what you do, you place wherever you want to place, whether in left hand side or maybe in the right hand side. Then finally you calculate or finally you estimate the cell potential. If the cell potential is coming to be positive, then the way you have represented is the right one. But if your cell potential is coming to be negative, then you should reverse the half cells. That is, this half cell will go over here and this half cell will go over here, over to the right hand side, to get you the positive positive cell potential. Okay. Now, next is the what is the relationship between the electrode potential and concentration of the electroactive substances. Now, recall that while we were discussing this standard electrode potential, then it was assumed that your electroactive substance, that means the electrolyte, the concentration is kept to unity, so that whatever half cell potential you are getting will be called as the standard reduction potential at say 298 Kelvin. Okay. Now, if we apply thermodynamics while evaluating the delta G of the chemical process, then from thermodynamics we can write, because we have to make use of this expression that delta G is equal to minus NFE E cell, and if you plug in this information to the delta G expression for a chemical reaction, suppose that chemical reaction is operative in the electrochemical cell, then you will end up in getting one expression which is known as the Nernst expression, Nernst equation. And for half cell you can write like this: phi m n plus m is equal to phi 0 n plus m minus R t by n f ln concentration of m divided by concentration of m n plus. Actually, the expression was developed with the in the numerator and denominator. Expression was developed with respect to the activity of m and activity of m n plus, but for dilute solution, you can replace activity with concentration. That is why we are writing like this. Otherwise, true expression is the ratio of the corresponding activities. Now, R is the gas constant, T is the absolute temperature, N is the number of electrons, that are involved in reducing the species. That means m n plus n electron, that gets you m. So, n number of electrons are involved in this reduction process. F is the Faraday, it is approximately 96500 coulomb per mole, 96500 coulomb per mole. Okay. So, therefore, for solids and gases, or if it is in the pure state of aggregation, this numerator will, and I mean for all practical purposes, you can take this to be equal to unity. Okay. That means activity is taken to be unity for pure state of aggregation. So, therefore, we can write phi m n plus m, that will come out to be equal to phi 0 m n plus m, then minus R t by n f ln 1 upon concentration of m n plus. Okay. So, where R is, the value of R is 8.314 joule Kelvin inverse, mole inverse for the value of R. Okay. And F is 96500. Okay. So, and here it is the molar concentration, mole per liter. Okay. So, this is the expression. Now, you see that the value of phi, means it is not the standard, but this is the standard potential. So, value of phi will depend on a constant quantity at a given temperature, say 298 Kelvin. It will also depend on the concentration of this species. So, if it is changed, then accordingly the value will be modified. Okay, if it is changed. So, therefore, it depends on this one. It also depends on the temperature. So, that is why in electrochemical experiments, temperature is very important quantity, because temperature, if you change temperature, automatically standard states and everything, I mean with respect to standard state, your state of measurement will be changing. So, therefore, this phi will be changing. So, therefore, temperature is important, and maybe for changing temperature, the change in phi may not be that huge, but still there can be some change in the value of phi as you change the temperature. Okay. So, this is basically the standard reduction potential, and this standard reduction potential, how to measure, I already explained to you I mean while discussing the construction of cell with standard hydrogen electrode. Okay. So, let us look at some standard electrode potential, reduction potential at 298 Kelvin of some substances. So, standard electrode potential at 298 Kelvin and your E 0 bar in volt. Okay. So, if the reaction is F2 gas plus, so we will just discuss with the reaction involved, that is the reduction reaction involved, 2F minus, its value is 2.87. Then take another H2O2 plus 2H plus twice electron, that gets you 2H2O. Okay, its value is 1.78. Okay, Cl2 plus twice electron, that gets you 2Cl minus, its value is 1.36 volt. MnO2 solid plus 4H plus twice electron, that gets you Mn2 plus twice water, its value is 1.23 volt. Cu 2 plus twice electron, that gets you Cu solid, its value is 0.34. Okay. 2H plus twice electron, it is H2, it is assumed to be, I mean, at all the temperatures 1 bar pressure, it is equal to 0. Fe 2 plus twice electron, Fe 0, Fe solid, it is minus 0.44 volt. Zinc 2 plus twice electron, that gets you zinc solid, it is minus 0.76. Sodium plus electron, that gets you Na solid, minus 2.71. Then lithium plus electron, that gets you lithium solid, it is minus 3.05 volt. Okay. So, you see that there is a changeover from, I mean, it is the reduction potential. So, I have expressed the reaction as the reduction reaction, you see it is all represented as reduction. So, reduction potential, you see that the value is reducing this way, So, positive value of the redox couple with respect to, so it is positive means positive with respect to 0, negative means negative with respect to 0. So, positive means it is a weaker reducing, okay, it is a weaker reducing agent compared to hydrogen. Negative means it is a stronger reducing agent than hydrogen. Hydrogen means this, you know, H plus H2, half H2 system. So, that means you can say that higher the value, higher will be the system will have higher tendency, larger tendency to remain in the reduced state. Higher the value in absolute sense, because you have to consider both, I mean the numerical value as also the sign. Okay. So, higher the value, higher will be the tendency to be reduced. You see that this fluorine gas, so it is that in reduction scheme it is fluorine to fluoride, it is plus 2.87, consider this one for hydrogen. Okay. So, that means it is a positive value, the system will have the higher tendency, much higher tendency to remain as fluoride. So, that means it will be a very strong oxidizing agent. Okay, it is a very strong oxidizing agent and weaker, very weaker reducing agent compared to this. Okay, so, as you move on to towards the hydrogen, you see that these values are reducing. that means their oxidation power, I mean the tendency to oxidize other material, it is reducing. Okay. And then it is, with respect to hydrogen, it is 0 means it is in the balance point, and then if you move on to this side, you see that sodium, you see its value is negative, its half cell potential is negative. Half cell potential negative means that corresponding phi value is negative, means the delta G value for this particular process is positive. Positive means the way it is represented, that Na plus to Na, this reaction is not spontaneous, however, the reverse reaction is spontaneous. Okay. That is why it is 2.71 with negative, means it will always try to remain as sodium plus. That is why you have to keep sodium metal inside kerosene, so that it does not get contact of water or some other agent. So, it is very reactive. In the same way, this is also very reactive. So, here this side is reactive, here the left hand side is reactive, depending on whether your this E0, or it is basically phi 0, I should write phi 0, this phi 0 is negative or it is negative or it is positive. Okay. Next is, so now for a Daniell cell, we started with the Daniell cell. So, for Daniell cell, cathode means it is right hand electrode, where the reduction is taking place. Okay. So, phi Cu 2 plus Cu is equal to phi naught Cu 2 plus Cu minus RT by twice F, because 2 electrons are involved, ln this 1 by concentration of Cu 2 plus aqueous. Anode, left hand electrode, oxidation, phi zinc 2 plus zinc. We are using the reduction potential values, that is why it is, I mean first zinc 2 plus, then zinc 0. So, process is from here to here. So, phi 0 zinc 2 plus zinc minus RT by twice F ln 1 by concentration of zinc 2 plus aqueous. Okay. So, therefore, what we get? What do we get? We get E cell. What do we get? We get E cell is equal to, again same thing, phi right minus phi left. So, this is UPAC as per UPAC and reduction potential. Okay. So, therefore, it is phi right minus phi left, means this phi Cu 2 plus Cu minus phi zinc 2 plus zinc. Okay. So, you just plug in this information, you write this one first. So, that means phi naught Cu 2 plus Cu, then write minus RT by 2F ln this Cu 2 plus aqueous this. Okay, so, this gives you this part phi, I mean this one minus this one, minus this one means minus this one minus phi naught zinc 2 plus zinc, okay. And then minus means this will be plus. So, plus RT by 2F ln this 1 by zinc 2 plus aqueous, okay. So, this together, okay, will get you. So, therefore, you can write E cell equal to. So, E cell means this one and then this one. So, bracketed one will be basically E0 cell, because it is the difference in the standard electrode potentials, and then E cell is E0 cell minus RT by twice F ln zinc 2 plus aqueous by copper 2 plus aqueous. So, this is the expression for E cell when you consider this this Daniell cell, okay. So, Daniell cell means it is basically the reaction is basically in the right hand side there is reduction, in the left hand side it is oxidation. So, net reaction is that, so in one electrode this zinc to zinc plus is happening, in other electrode copper to copper, copper plus 2 plus to copper 0. So, zinc plus CuSO4, that gets you zinc sulphate plus Cu, okay. So, and since these are pure state of aggregation, their corresponding activity or concentration value can be taken to be unity. So, therefore, you see that E cell depends on temperature and also depends on the ratio of the electroactive or electrode active species or the electrode with which it is reversible, that is the ion with which or against which this electrode is reversible. So, it depends on the concentration of that. So, if you plug in the value of R, F, and if you put T is equal to 298 Kelvin, then you will end up E cell is equal to E0 bar cell minus 0.059 by 2 log zinc 2 plus aqueous by Cu2 plus aqueous. So, this is the expression for the E cell for the Daniell cell. Okay. So, what we have learned? So, we have learned in this particular piece of lecture that with the help of standard hydrogen electrode, coupling with standard hydrogen electrode, and if you construct a cell with unknown half cell, then you will be able to find out the half cell potential, and then with this half cell potential, if you with this information about the various, the information means the information about various half cells, then you can pick up specific half cells to construct different types of cell, where the total cell reaction will be the combination of individual half cell reactions. Okay, so, this much for today. In the next lecture, we will take up some examples and some applications of this EMF measurements and some other aspect of this electrochemistry. So, till then, thank you.